pleasure to introduce Elliott Gesteau of the Laboratory of Einstein. So Elliott received his PhD in mathematics at Caltech last summer, where he researched the thesis titled Mathematics of Nonsensical. So his research lies in the interface of mathematics and so sorry for getting your affiliation on it, but Elliott actually does know us.
Yeah, that's right.
And he is going to start a position in the Center for Gravity and the Center for so Elliott will be around. And today will tell us talk title. But before you start, Elliott, I want to remind everyone.
Great. Well, thank you very much for the invitation. I'm very excited to present my research in this talk, which is titled, Who Can Observe a Closed Universe? Sorry, a technical problem. Still not working.
So, sometimes one.
Yeah, there's no mouse.
Oh. Yeah, maybe just press click and then no.
Okay. Yeah. Okay. So let's hope it works. Okay. So since this is a Black Hole Initiative colloquium, I figured that a good idea would be to remind everyone of one of the most remarkable features of black holes. Namely, one of the most remarkable aspects of black holes is that they possess an entropy. So the entropy of the black hole is given by the area of the horizon over 4 times Newton's constant of gravitation in natural units, where I've taken CNH bar to be equal to 1. And this was found in the 70s by Bekenstein and Hawking. They found that this quantity behaves a lot like an entropy in thermodynamics. And when you have something that behaves like an entropy, it has a very suggestive interpretation. Because as we know in statistical mechanics, the microscopic interpretation of entropy is that, if you have a system with a few macro parameters like temperature, mass, and so on, then it actually has a lot of micro states that live to the same macro parameter. And you can interpret this entropy as counting the log of this number of microstates. So you can think of this black hole entropy as the number of fundamental degrees of freedom that a black hole should have in quantum gravity. I want to stress from the get-go that this statement is counterintuitive, okay? And it's bound to lead us to surprising outcomes. Because if we just put a field theory in the interior of a black hole, naively, we would expect the number of degrees of freedom of that field theory to scale like the volume of this interior and not like the area of the horizon. It looks like there's way too many degrees of freedom in the black hole. So a lot of questions that we're asking in quantum gravity can be traced back to this question. What are these fundamental microscopic degrees of freedom of a black hole in quantum gravity? And why are there so few of them? Why don't we get a volume scaling? Why do we only get an area scaling? So finding the notion of black hole entropy was very fruitful in our understanding of quantum gravity, and it was later generalized by this notion of the holographic principle, which 't Hooft and Susskind proposed in the 90s. So the holographic principle states that the number of degrees of freedom in a well-defined region of space is given by the area of the boundary of that region over 4g Newton. So you can sort of see this as a generalization of the statement of black hole entropy for more regions of space. So perhaps a lot of you have seen these types of pictures where you can really imagine that region of space being entirely described by some bits of information on the boundary that can take the value 0 or 1, and this little fundamental unit of area on which one bit of information lives would be like the Planck area. Okay, so holography is great, and by now we have a lot of theoretical evidence for it. So one of the earliest precise things that were done is a microscopic realization of black hole entropy in string theory by Strominger and Baffa. So this was done in a precise setup of a certain kind of supersymmetric black holes, and what they were able to do there is to exactly count the number of microscopic degrees of freedom of that black hole and find that it matched with the Hawking prediction. There's also been generalizations of these sorts of entropy calculations for more regions of space-time by Bousseau, which lead us to believe that the principle should be more general. But perhaps, the strongest piece of evidence we have for holography is the so-called ADS-CFT correspondence. So the ADS-CFT correspondence is the first example of a full holographic duality that was found by Maldacena in 97. And so what it equates is two descriptions of the same system. One description is a bulk description given by string theory in this asymptotically ADS background. So here you can see that you have this solid cylinder, which is NT de Sitter space, and you put some string theory in it. And it turns out that I can describe the same quantum gravity theory by using another language, which is a boundary description, which is a conformal field theory that lives on the boundary of the cylinder. Okay, so this is really a duality because both the bulk description and the boundary description are entirely equivalent. They describe the same system. They're just two different languages to talk about the same thing. Okay, and that really tells us that we can equivalently think of this quantum gravity theory in NT de Sitter space as being purely encoded in the boundary of that space. So holography is great. It's been teaching us many lessons, in particular about the evaporation of black holes, which I guess a lot of people here care about. And we will mention some of that in the talk, but there is one case that hasn't been so studied in the context of holography compared to the other ones. And that's the case that I'm going to be mainly interested in today, is the case of a closed universe. So what's a closed universe? Well, a closed universe is a universe that doesn't have a boundary at spatial infinity. So to contrast with the previous example, if we had this cylinder representing NT de Sitter space and the vertical axis was a time direction, if I take a space slice of the cylinder, it's a disk. So this disk has a boundary because there's a circle at the boundary of this disk. So NT de Sitter space has a boundary. It's not a closed universe. But you could imagine that instead of having this disk, we would have a sphere as the space slice of our spacetime. And then, of course, spheres don't have boundaries, which means that spheres are a closed universe. One of the main examples of a closed universe is de Sitter space. De Sitter space is a spacetime with positive cosmological constant, and each space slice of this space is a sphere. So because it has positive cosmological constant, it's very relevant phenomenologically because we have a positive cosmological constant in our own universe. And for all we know, our universe may very well be closed. At least a lot of models of cosmology are based on de Sitter space. So this makes it a very relevant question. But if we try to apply the principles of holography to the case of a closed universe, at least a naive application will very quickly make us run into a very serious problem. So let's try to run the holographic principle that I just stated in the case of a closed universe. We said that in quantum gravity, if we believe that the holographic principle is very generally true, if I take a given region of space, the number of degrees of freedom of that region of space should be equal to the number to the area of its boundary over 4 times g Newton. We just said that by definition, a closed universe like this doesn't have a boundary. So the area of the boundary is 0, and the statement seems to be that this closed universe has 0 degrees of freedom. Okay, so if we take the holographic principle at face value, it seems that there is no degree of freedom of quantum gravity in this space. Now, people noticed this for a long time. It's not a new remark. But I guess it's fair to say that for a long time, people weren't too worried. After all, we don't have a perfect understanding of holography, especially at the time when it was first noticed. There was very little understanding of holography. So it was easy to dismiss this by saying, okay, well, maybe there's something that we're missing about the holographic principle that just tells us that we're not able to apply it to a closed universe directly. And this was sort of the consensus for a long time. But what I will try to argue in this talk is that in recent years, there's been sort of a very strong mounting body of evidence from what we've learned about holography that tells us that maybe there's something deep behind this claim. Maybe it's not just a bug of our understanding, but it's actually a feature of quantum gravity. Of course, this sounds crazy, and the rest of the talk is going to be trying to make sense of how such a statement could be true. And in particular, there's a way to rephrase this statement mathematically, which is that if we want to ascribe a Hilbert space to a closed universe, as we like to do in quantum mechanics, then if the closed universe has no degrees of freedom, the rule is that the dimension of this Hilbert space should be e to the number of the degrees of freedom. So here it's equal to 1. Okay, so the statement we're going to try to make sense of today is that a closed universe may have a one-dimensional Hilbert space in quantum gravity. So how is this going to go? Well, first, I would like to give you a flavor of why we believe that this may not be such a ridiculous claim after all. So I want to give you some evidence that comes from recent developments in holography about why we believe that this may actually be the case. And then once I've given you at least some of this evidence, I will switch gears and try to make sense of this statement. And we will see that in order to make sense of this statement, we may need to come back to the axioms of quantum mechanics, and in particular to the role that the observer plays in the axioms of quantum mechanics. And because this is a rapidly expanding field with a lot of excitement and high energy at the moment, I want to end this talk by giving some outlook on some future directions that I think we should be on the lookout for in the next few years. Okay, so let's start with the evidence. There's various arguments for this statement that the Hilbert space of a closed universe is one-dimensional. I'm not going to go through all of them in detail today. I'm just going to present some of them and then describe the other ones briefly at the end. The reason why I chose these arguments is that I think they already sort of contain the seeds of the answer of what we need to be doing next. There's another more pragmatic reason, which is that the arguments I'm about to present are very closely related to the physics of black holes, and this is the theme of this talk, so this is a good fit. In particular, the first argument I want to give is based on evaporating black holes. So this is something that hopefully a lot of people here care about. Okay, so evaporating black holes. Classically, we would think that nothing comes out of a black hole, but what Hawking told us in the 70s is that actually, if you take into account quantum effects near the horizons, this is not true. Black holes very slowly evaporate, and this is due to the thermal nature of horizons. Black holes actually have a temperature, and the quantum fields near the black hole create some form of evaporation. So this evaporation process is, to very, very good accuracy, thermal. Okay, it's just black body radiation due to the temperature of the black hole. So here I drew the Penrose diagram of an evaporating black hole, and I drew different slices on it. So this is the asymptotically flat boundary condition of this black hole. It's not very important, but I chose it to be asymptotically flat here. And then I took different slices of space of this black hole. So this first space slice here, this green slice sigma 0 is taken before the black hole forms. So let's say you have a star in the bulk or something like this. No black hole has formed yet. But as I go in time, an event horizon forms. So this is this diagonal line here, and then you have the singularity in the interior of the black hole. On the slice sigma 1, we're somewhere in the evaporation process. So the black hole has started evaporating, but it's not fully evaporated. There's still a horizon. And then if you wait very, very long, at some point the black hole will be fully evaporated, okay? And this upper part of the diagram will not contain any black hole anymore. So the second slice that I chose to draw was sigma 2, which is this blue slice. And you can think of the exterior portion of sigma 2 as containing all of the radiation that the black hole has emitted once it's fully evaporated. The reason why I also drew this sort of interior part of the slice is because we will see that this is very closely related to the notion of closed universe. The reason is that here you see that the interior disconnects from this exterior slice at the singularity. So you can sort of think of this interior portion of the slice as a closed universe. So a bit more precisely, let's talk about what happens on this slice sigma 1 where the evaporation process is happening. Well, at each step of the evaporation process, what happens is that a particle makes it to the exterior and it remains entangled with the inside. Okay, so you keep emitting more and more particles that are emitted entangled with the inside. The reason why we care so much about evaporating black holes is the information paradox. So here is the simplest way of stating the paradox. At the beginning of evaporation, so shortly after the sigma 0, when we're right before the horizon forms, the black hole is in a pure state. Okay, because we just have one state of the whole quantum fields on top of the spacetime. And but then we just said that the Hawking process is thermal. The particles that are emitted at each step are emitted in a thermal state. They're entangled with the interior. And because of this, at the end of evaporation, if I look at the state of the radiation that I've collected on this exterior portion of the blue slice, then it's actually in a thermal state. But now this violates what we know, because the first thing we know is that the thermal state is never pure. It's always entangled to something, or at least you can entangle it to something. And the second thing we know is that in quantum mechanics, unitary evolution always takes a pure state to a pure state. So if we start with a pure state of things that go into the black hole, then when everything comes out, it should be in a pure state, yet Hawking tells us it's in mixed state, so that's a paradox. A more precise way of thinking about this paradox is in terms of this so-called page curve. So what you can do is study the entanglement entropy of the Hawking radiation throughout the evaporation process. Okay, so the radiation, as it gets emitted, is always entangled with the interior, as it says, and this quantity, the entanglement entropy, measures how entangled the whole set of radiation is entangled with the interior. So if you trust Hawking's calculation, then you would just find this green curve here. The reason is that, so the x-axis is time, the y-axis is entropy, entanglement entropy, and the more Hawking quanta you emit, the more entanglement you're supposed to have between the radiation and the interior. So the curve goes up. On the other hand, we know something else, which is that the entropy of entanglement of the radiation cannot be larger than the maximal number of degrees of freedom of the system it's entangled to. And here, the system that it's entangled to is the black hole. So by the holographic principle, by black hole entropy, we know that the entropy of a black hole, the number of degrees of freedom of a black hole, is the area of the black hole over 4G. So we can also study during the evaporation process the evolution of the area of a black hole over 4G. And it turns out that it actually goes down because the black hole is shrinking, so its area, the horizon area becomes smaller. And in particular, there will be a point where these two curves, the entropy of the black hole and Hawking's radiation's entropy, will cross. This point happens near, very roughly speaking, near the middle of evaporation. And this is the point where the paradox starts kicking in, okay? Because Hawking's calculation tells you that you're more entangled than you're allowed to be to the black hole. So a paradox shows up at this so-called intermediate time called the page time. One thing that I want to stress is that this page time happens way before the black hole is evaporated. It doesn't happen when the black hole horizon is small. So we can't just say, oh, there's something we don't understand because when the black hole just finished evaporating, there's some Planckian effects happening and we don't have any control over that. It's really a paradox that has to do with a scale where the black hole is still macroscopic. So we would expect to trust effective field theory near the horizon, which is part of why this paradox is so deep. Okay, so we were, very confused about black hole evaporation for a very long time. We were very confused about the page curve. But in 2019, there were two breakthrough papers that derived a very important result.
So is this page time uniquely defined?
Yeah, it's defined as the time where these two curves cross. Yeah. So in 2019, there was a very important step made towards understanding this paradox. In particular, what was done in these two papers is that it was found that we can actually directly derive the page curve from a gravitational calculation. I'm not going to go through this calculation in any detail. I will just say that recent developments have been able to derive this page curve from what we know about holography. But what I do want to tell you is one of the main conceptual lessons that we've learned from these recent page curve calculations. And the main conceptual lesson is that after the page time, it is not right to think about the interior of the black hole and the radiation as separate systems. Naively, we would think that they are because they're very far from each other. If I take two chairs in this room, they're separate systems. It turns out this is not true for evaporating black holes. So they're the same physical system. You can think of this as a new case of duality. In the case of ADS-CFT, we knew that there was one physical system that we could describe in two ways. One of them was the string theory in ADS, the other one was the CFT. Here it's the same. We have one physical system. One way to talk about it is the black hole interior. Another way to talk about it is some subset of this Hawking radiation that has been emitted. So I insist, it's not about how entangled they are. The interior is literally a subsystem of the radiation. And then, because it's a subsystem of the radiation, what was found is that in particular, if you want to describe things like effective field theory in the interior, you can actually see all of that just by looking at the radiation up to very small errors that are controlled by e to the minus the black hole entropy. And of course, when you have corrections that, yeah, sorry?
Are you saying that at the page time, instantaneously the entire interior becomes a subsystem of the exterior?
Well, there's a phase transition. I'm not sure about exactly what happens at this phase transition, but let's say we're reasonably after the page time, then yeah, I think there's a duality that shows up there.
Is that also a duality of the
Holography? I mean, is this a version of holography?
I think you can really see it as a version of holography. Yeah. Just like ADS equals CFT, like it's not right to say, oh, we have a CFT on the boundary and we have the gravitational system and they're different. They're just the same thing, two different languages to talk about the same thing. Here is the same. You have two languages to talk about the same thing. Yeah.
Would you talk about like the idea of this error estimation?
Yeah, sure. I mean, you can. Yeah, basically the idea is that these errors are going to come from subleading saddles in the gravitational path integral, and they're exponentially suppressed in 1/g Newton. Okay, so you know these errors are very small. Okay, we don't expect effective field theory to hold in our own universe when we reach such scales that are exponentially suppressed in G. So you can really think of the radiation as describing a system of quantum gravity that is to good accuracy semi-classical, and there's no more paradox. Okay, so on this slide sigma 1 here, where the black hole is past the page time but still very far from full evaporation. This conceptual resolution sort of solves the tension by identifying the radiation with the interior. However, this is all great. This was a very beautiful development, but what I want to stress out is that this works really well when you're past the page time, but the black hole horizon is still macroscopic. Okay, this slice sigma 1 here is not taken at the evaporation point. It's taken before the evaporation point, where you still have a non-zero area for the black hole, an area that's order 1. On the other hand, you can look at what happens at the end of evaporation. And here, you know, you can see that something seems to be going wrong, seems to be breaking in this picture. So what happens at the end of evaporation? Then we said that we have this slice sigma 2. So the analog of the interior would be this disconnected portion of space-time through the singularity that we can sort of think of as being a closed universe. And then you have the exterior, which contains the whole radiation here. So yeah, we can think of this interior as a closed universe. But now we said before that the errors in the reconstruction of semi-classical physics in the interior were controlled by e to the minus a over 4g. Yep.
If I choose, let's keep the slice outside the black hole fixed. Would the story change if I chose the part inside to be the horizon?
Well, you would then you mean you would want to cut through the horizon here?
No, I mean actually running null along the horizon.
Running null? I don't know. I guess you could see it as a limit of the case I'm drawing here. I'm not sure something terribly different would appear, but I really want this to be space-like though. So I don't know.
But the parent horizon isn't null, right? The parent horizon becomes time.
The apparent. Sorry, were you talking about the apparent horizon?
No, but yeah, that's true.
Okay, yeah. So I definitely don't want things to be time-like. Okay. So yeah, so we can think of this interior as a closed universe that branches through the singularity off from this exterior. And now we said that, you know, semi-classical physics is well described by the radiation. Like if you look at the radiation carefully, you see that the black hole interior, which is the same as the radiation, is semi-classical up to very good approximation, which is e to the minus a over 4g in the slice I drew before. But now on this slice, the area of the horizon is 0. Okay, it's no longer a big number. So the error that was exponentially suppressed in this very large number a over 4g now becomes a pretty bad error because a over 4g is 0. So this whole idea of saying that you can reconstruct semi-classical physics inside the black hole well on this slice by just looking at the radiation seems to break because you're making errors. Another way of saying this, perhaps for people who've been following this a bit more closely, is that usually in this page-time story, you say that the semi-classical observables that make sense from this holographic description after the page-time are the ones that are sub-exponentially complex in a over 4g. There's a lot of them when a over 4g is big, but when it's 0, there's nothing that's sub-exponentially complex in 0. Okay, so all of this tells us that no physics, or at least no semi-classical physics in the interior, can be reconstructed from the radiation. Okay, the radiation is actually telling us that the interior isn't there. It's just a very, very quantum object. Perhaps a slightly more a closer way to what I was saying before to say this is that only a one-dimensional Hilbert space of states is encoded in the radiation. If you trust the holographic description given by the radiation, it will tell you that the Hilbert space of the closed universe is one-dimensional. Okay, so in particular, the Hilbert space of the radiation contains no interior. Yes?
Sorry, it seems to me like the argument you just gave implies like the Hilbert space of the closed universe is like order 1, but not actually 1.
Good, good. Yeah, okay. So you can actually do a more precise calculation and see that, yeah. Oops, sorry. Yeah, well, another way to say this, I guess, is from this, from this point of view of complexity, right? You want to allow for only observables in your Hilbert space that have a complexity that's small compared to a given number, but here the number is really 0. The area is 0 on the nose, so there's no observable. Okay, so we seem to be seeing here a breakdown of semi-classical physics, and we can see that the Hilbert space of the closed universe in the radiation is one-dimensional in this example. Yes.
Yeah. So right. So if I took the Cauchy surface, or the surface for the initial data surface for the interior that you've drawn there, and I deform it so it runs almost along that null surface there. But yeah, let's see. I don't need it to go completely null. I'm just confused by the statement that I would think that's a good initial data surface for the semi-classical interior.
That's right.
And I can deform it so it's very far from the singularity.
Yeah, that's the confusing thing, right? This portion of the slice is far from the singularity, but if you're looking at the radiation, it looks like this portion of the slice is just not semi-classical.
Right.
That's the confusing point.
Okay, good. Yeah, and that because I think I would, if someone comes to me and says they've solved the black hole information paradox, I think I would like to reconstruct the semi-classical dynamics of the interior given the late time Hawking radiation.
Maybe in the last section I can tell you maybe how to do that. Okay. We will see if you buy the argument. Okay. Okay, so this was one argument based on evaporating black holes. I really like this argument because it really draws from the important lessons we've learned about quantum gravity in recent years. I also like it because it has to do with one of the most popular setups, the setup of evaporating black holes. But there's various things you could complain about when you look at this argument. For example, if you're general relativist, you know that because the slice sigma 2 that I drew cuts through the singularity, you get to a point where you have Planckian curvatures, you have divergent curvatures. It's not a nice slice. So you could be tempted to say, well, this is an artifact of the fact that space-time becomes singular at the disconnection point. It's not smooth disconnectivity, and so maybe that comes from there. So it's not an airtight argument. However, what I want to tell you now is that there's another family of arguments that can be given directly within the ADS-CFT correspondence. So in a setup that's completely controlled, where we can actually show some things at a mathematical level of rigor that leads us to the same conclusions. Okay, so just a bit of background on the ADS-CFT correspondence. The bulk description of the system is this type 2B superstrings on ADS5 cross S5. The boundary description is n equals 4 angles with an SUN gauge group. And you can think of the n here in the SUN as being the number of degrees of freedom of that boundary theory. Okay, and G, so Newton's constant in the bulk, is identified with 1 over n squared. So in particular, if you want to be in regimes where GH bar corrections are small and so on, then you want to take n to be very, very large. So in this n very, very large, the bulk physics, the bulk description is supposed to look a bit like our own space-time. So an emergent space-time background that satisfies Einstein equation and then some fields on it with semi-classical physics valid in this background up to exponentially small corrections in n. Okay, so within the context of this ADS-CFT correspondence, it was recently realized by Antonini, Societa, and Swingle that you can actually construct a state that looks like it carries a closed universe in the bulk, that looks like its bulk description contains a closed universe. So the setup is the following. You take your two CFTs. So here, this would be my left CFT. This thing would be my right CFT. And you entangle them in a so-called partially entangled thermal state. So the formula for this state is the following. You sum over the energy eigenstates, and the matrix elements are given by a product of first an insertion of heavy operator here. So this operator OAB is a heavy operator of dimension n squared. You can see it as being inserted here in the Euclidean past. And then you have these Boltzmann suppression factors, because this is just a modification of the thermal state. I'm especially interested to see the state in temperatures that are below the Hawking page transition. It's going to be very important that we take these inverse temperatures so that the temperature is low. The temperature is below the Hawking page transition. And it turns out that, if you consider this heavy operator like a heavy dust shell that you insert in the bulk and you solve Einstein's equation, in this regime of temperatures, what Einstein's equation predicts is 2 copies of ADS in Lorentzian signature that are entangled with a closed universe here in the middle. So this is a crunching cosmology. So, if you do the usual rules of gravity, of Euclidean gravity, this is what gravity predicts for you. So this state is interesting because it looks like it's an exciting setup to study closed universe. Yeah. Sorry?
What are the axes? I don't understand.
Okay, yeah. So you're cutting here. Below here is the Euclidean preparation.
Oh.
And here is the Lorentzian continuation. Yeah, maybe I should have said that. Okay, yeah. So yeah, the Lorentzian picture of the spacetime is really the top part, and it contains 2 copies of ADS and a closed universe.
Okay.
Yes.
Sorry. What is operator O realized like in the form?
You can model it like a heavy dust shell.
It's like using perfect fluids on the shell.
Yeah, I mean, you can put, basically what you do is that you say you have like a delta function source in your Einstein equation, and then you solve for the gluing condition.
I see.
Yeah.
The details are not super.
Oh, yeah, sure.
Yeah.
Is this closed baby universe macroscopic?
Micro or macro?
Macro.
Macro, yes, it is. You can show that it actually has order 1 size, like it's not a small thing. Yeah. Okay. So now, now the state looks very good because it looks like you can prepare a baby universe. But shortly after, it was noticed by Antonini and Roth that there's a pretty serious puzzle about this state. The crucial point is that we said that the temperatures of both CFTs are taken to be low. They're taken to be below the Hawking-Page ratio. And because of this, you can show that this state actually has order n to the 0 energy. It has an energy that doesn't grow with n. And so essentially, at least if you wave wave hands, then you would say that it's a finite excitation of 2 copies of the vacuum. You can truncate it to very good accuracy to a microcanonical window of finitely many energy states that doesn't grow with n, and it's just a finite excitation of the vacuum. But then this is very strange because such states are actually the simplest ones in ADS-CFT. They're the states we understand the best because they're just finite excitations of 2 copies of the vacuum. And by the extrapolate dictionary, we would think that finite excitations of 2 copies of the vacuum are just 2 entangled copies of ADS with no baby universe in the middle to be found. Okay, so there's this paradox that if you trust, so Netta likes to say that the baby has been thrown out with bathwater. It looks like you have a baby universe when you do the gravity calculation, but actually when you think about the state from a CFT perspective, it looks like there's no more baby. So what's happening? So this is a strong puzzle. In particular, the question arises of which description is actually correct. Is it the gravity calculation? Yeah.
Wait, I didn't understand why they give different answers to some question. Why is this a puzzle? It's not just 2 descriptions of the thing.
Well, okay, so indeed, that was proposed as one of the solutions to that paradox, which is that, okay, maybe we can describe the same state in 2 different ways that are equivalent. One of them has this baby universe, the other one doesn't. On the next slide, I will tell you that there is at least one way in which we cannot say that the 2 states are describing the same thing.
So it means ADS is not equal to CFT because you have multiple bulk states that look the same as CFT. I don't want that anymore.
But there's quantum entanglement, right? What's the?
Maybe I should go to the next slide.
Okay, yeah.
Okay, so we have these 2 states, right? There's this first state which has these 2 ADS. So now everything is Lorentzian signature. So I have these 2 ADS copies, and they're entangled to the baby universe. In the other case, there is just these 2 ADS copies that are entangled to each other. So there is something very different in these 2 semi-classical descriptions, which is that in the case with the baby universe, we can look at the system of the 2 copies of ADS. And it's in an overall mixed state because it's entangled with the baby universe. On the other hand, in the case without the baby universe, we can look at the system of the 2 copies of ADS again, and it's in an overall pure state, okay, because it's not entangled to anything. in ADS-CFT, we know that the fields on this semi-classical geometry can be described by the large N limit. We can reproduce their correlators in the large N limit and ask if these correlators are the ones of a pure state or the ones of a mixed state. And there should be an answer to this. It's not like there can be two answers to this. The large N state cannot be pure and mixed at the same time for these operators that live on the ADS spaces. So it turns out that, yeah, so the first thing is that these two cases can actually be distinguished by a simple operator in the large N limit. And we could compute it in some qubit models and show that it agrees with the case with no closed universe with Netta in a paper from a few months ago. And then very recently, I was also actually able to show a no-go theorem, which takes no simplifying qubit assumption or anything like that, and just tells you that if an order N0 energy state has a large N limit, then the two copies of ADS will always be in a pure state. They cannot be entangled with a closed universe. Okay, so at least from the point of view of the traditional rules of ADS-CFT, with the large N limit, the answer seems to be the second one. This closed universe is not actually that. Yes?
Are you saying that there's some calculation you can set up where you can compute correlators on the baby universe? Is that what you said?
Okay, two things to this.
Semi-classical.
Yeah, so it's a bit more. It's a bit more abstract than that. Are you talking about the proof of this no-go theorem, or?
No, I'm just asking whether in this setup, there's some context in which we could have a semi-classical description of the baby universe and compute correlators.
Oh, okay. Are you talking about the bulk description? Like, let's say we want to do
I
this.
just want to know if there's any.
Yeah, so there's been a few computations.
We can do that.
Yeah, so there's been a few computations of correlators in this baby universe from the bulk perspective, and then people have been trying to match it to the CFT. I'm not sure if it works, but if it works, it's not the regular ADS-CFT that they're doing. I'm going to go into that into a bit more detail at the end of the talk.
But if you can't do that, you can't really say there's a macroscopic baby universe in there, right? It's just some.
Right. It's just the gravity computation that you usually do by doing, the Euclidean preparation, and then you solve for Einstein's equation in the bulk is misleading you. Even though it looks like there is a semi-classical baby universe when you do the gravity computation, that's inconsistent with the rules of ADS-CFT. So we shouldn't trust this gravity computation.
I'm confused by the statement that the two could be distinguished with a simple operator. I don't really have a good intuition for this, but I guess I would have. What prevents one from, encoding the baby universe in some very complicated way?
What prevents you is that everything doesn't scale like n here. Okay, usually in ADS-CFT, when you say complex in n. Here, because the state is of order n to the 0 energy, everything is order 1. The entropy of entanglement, for example, between the closed universe and the rest of the system is order 1. So all these sort of complex things that were saving us in the black hole information paradox story cannot happen here, because we're looking at something that cannot carry any complexity, I think is the answer. So it's really about the n scaling of the energy of the state.
Just like once the black hole is fully evaporated, you can do a swab test on the radiation and see that it's pure, and it's a very easy thing to do. The black hole is fully evaporated. No high complexity requirement.
Yeah, so here it's not completely fully evaporated, but at least, in the black hole evaporation case, you have an entanglement with the interior that needs to be growing with 1/g for there to be a solution. Here it doesn't grow with 1/g because it's of order n to the 0. So it's almost fully evaporated compared to the other case. Okay, so yeah, maybe I should just say that in a similar way, the outcome seems to be that whatever semi-classical physics there is in this baby universe, it actually cannot be encoded in the CFT by following the traditional rules of ADS-CFT. Okay, so instead, if we follow the traditional rules of ADS-CFT, we find that the right solution is this one, in particular because it's in an overall pure state. That means that it's never entangled to anything. And the biggest Hilbert space that I can entangle it to, which would describe this closed universe, is once again of dimension 1. You cannot have any entanglements with anything else. Okay, so again, we seem to be finding the same conclusion. Let me just, before moving on to the next part, yes?
Could you alternately interpret this as saying that, going back to the first transference, that this result says that we shouldn't have thought of it as a big universe in the first place.
Yeah, at least in ADS CFT, we shouldn't have thought of it as a baby universe. I think this is true. Now, of course.
So then it's not really.
Not emergent from the CFT.
What?
It's not emergent from the CFT.
If you use the traditional rules of ADS CFT, you take the large N limit and then you ask what is the background that emerges in this large N limit. As Nada was saying, this background will not contain a baby universe.
It's not what?
This background will not contain a baby universe.
Okay. But is that evidence that closed universes have a one-dimensional Hilbert space, or evidence that you can't describe them in ADS CFT?
So the point that I want to make next is that those two things are actually closely related. Because, okay, maybe let me.
Not being able to describe it in ADS CFT doesn't constitute a proof of it.
It's not proof. And I'm not saying it doesn't exist. I'm going to argue for the opposite afterwards. But at least, yeah, you can describe them in ADS CFT, which, is already a non-trivial statement. Like we could have assumed, we could have thought, because we know that sometimes the entanglement wedge reaches so far within the bulk that we would be able to describe a closed universe in ADS CFT. It turns out it's not the case. For example, we can describe the black hole interior after the page time, which is completely causally disconnected. Turns out when you have a closed universe, this is not possible. So something seems to be very different. Okay, so just I want to go quickly over some other arguments that point in the same direction. So these arguments tend to attempt to be a bit more general than the ones I gave you here. For example, they don't just use ADS CFT, they say general things about general setups. Of course, the price you have to pay is that if you try to be more general, you'll also be less precise and there will be more possible loopholes to the argument. So I'm not going to describe them in any detail, but for example, Euclidean wormholes have been crucial to the derivation of this page curve. And you can show using arguments based on Euclidean wormholes that, once again, you predict the 1D Hilbert space. Yes?
Don't we need those Euclidean wormholes have big universe cross sections? Don't we need them to have lots of states to carry the information from the interior described?
Well, I think the point is that the wormholes, whenever you do computation with wormholes, you're really, the current interpretation at least is that you're really computing an average quantity. And so the computation that can be set up here is that if you use the same techniques that were used for this page curve derivation, and you compute the average of the dimension of the Hilbert space of a closed universe that you prepare with Euclidean wormholes, you find that the average is 1. And then you can also compute the variance of this dimension using Euclidean wormholes, because it's again an ensembled quantity, and this variance is 0. And so you find this. Then there's another argument based on the quantum extremal surface formula, which is also a very important formula that was used to come to these page curve derivations. And it turns out that if you naively try to apply the quantum extremal surface formula to a closed universe, so there's a leap of faith there, which is that the setup is not the setup in which we've been able to derive the quantum extremal surface formula. But if you naively try to apply it to the case of the closed universe, once again, you get a one-dimensional Hilbert space. There's also a swampland conjecture that there is no global symmetry in quantum gravity. And it can be shown that for more than one state of a closed universe, you actually have an exotic form of global symmetry. So you can also exclude it from that. Yes?
So from the CFT point of view, if there was a baby universe, I think I would expect that under some coarse graining of the CFT algebra, you get some effective product algebra. Like, is that something that people have looked at to see whether or not there's a...
I'm not sure what you mean by product algebra, but I will talk about coarse graining at the end of this talk. So maybe you can tell me if that rings a bell. Okay, so this was the evidence. And, one thing that sort of came about when we gave these arguments about the evaporating black hole and the closed universe in ADS CFT is that, as Andy was pointing out, really, it looks like what we're actually saying when we say that the Hilbert space of a closed universe is one-dimensional is that if we're looking at a holographic dual that is disconnected from this closed universe, you can only encode one state of that closed universe inside that holographic dual. So that makes the statement a bit more precise. And it's actually reminiscent of some things that show up in the axioms of quantum mechanics. So I want to describe this now. In quantum mechanics, a physical system is described with a Hilbert space undergoing unitary evolution. Okay, that's what we all know. This is sort of the starting point of the game. And the number of degrees of freedom of that system can be thought of as the log of the dimension of this Hilbert space. Then the other really important part of the axioms of quantum mechanics is that the probability of an observation by an external observer to the system is then described by the Born rule. Okay, and those are our axioms. This is how we play the game. One point that I want to stress is that in the axioms of quantum mechanics, the observer is never part of the system. At no point are we allowed to put the observer in the system. Usually this is completely irrelevant because if we do any experiment in the lab or if we look at the sky, we're never part of the lab, we're never part of the sky. Okay, so that's why this is not a relevant thing. But when you try to think about a whole universe, you're part of this whole universe. So the thing is, maybe this is what we're missing. Could this be important? Could it be that secretly the whole time we've been putting this Heisenberg cut between the observer and the rest of the system at a place where actually the observer is not part of the closed universe? Well, this is actually the case. So in ADS-CFT, the ADS-CFT correspondence implies a duality between Hilbert spaces. Okay, when we say that the two systems are the same, what we're really saying is that the Hilbert space of the bulk theory is the same as the Hilbert space of the boundary CFT. And because we've picked a Hilbert space, we've already done a Heisenberg cut. We've already put the observer outside the system. So in ADS-CFT, you should really think of the observer as sitting outside the system. You can think of them as observing, the string theory or the CFT in the lab. So importantly, they are not part of the bulk gravity theory. Most of the time, this hasn't been very important, because we've seen that in traditional cases of ADS-CFT, or actually even for the black hole interior after the page time, as long as you're not disconnecting through any singularity, the interior is encoded really well into the CFT. The space-time is encoded really well into the CFT. Another way of saying this is that the space-time emerges from the CFT. So it doesn't make that much difference whether your observer is inside the space-time or not. It's because you can reconstruct their experience to very good accuracy. This was shown to some degree of detail in these black hole evaporation papers. However, we saw that in the case of a closed universe, this encoding of semi-classical physics in a closed universe inside the CFT breaks. So this is a place where it could actually be important and where we should maybe no longer trust the CFT to tell us about the experience of an observer in a semi-classical closed universe. The story in the information paradox is very similar. So there's a similar situation. The paradox arises to someone observing the radiation from the outside. Okay, when we compute the page curve, we're always looking at the radiation and trying to figure out how entangled it is. But the person is always observing the radiation from the outside. And in particular, they're trying to make predictions about what happens in the interior using this duality between the radiation and the interior, but they're not actually in the interior. Now we said that up to the very late stages of evaporation, where the observer is entirely irrelevant, because once again, you can actually talk about the interior really well by just looking at the radiation, because it's emergent from the radiation. It's encoded in the radiation up to errors that are suppressed in the entropy of the black hole, where we would expect semi-classical physics to fail anyway. But what we saw again is that when the black hole is fully evaporated, where it disconnects into a closed universe, this distinction becomes important. Yes?
When you talked about the information paradox, you never said the word observer, right?
No, because I want to define it now.
But why is an observer a fault? Because you can phrase it without saying the word observer.
What, sorry?
You can phrase it as you did,
just
as a question of whether pure states evolve with pure states. You never have to say in
no.
Heisenberg's formulation.
Yeah, maybe let me qualify this sentence a bit more precisely.
Okay.
What I mean is that the information paradox, what the recent lessons about the information paradox told us is that we can reconstruct semi-classical physics in the interior from the radiation, as long as we're talking about a slice that cuts the black hole when the horizon is still macroscopic. But what I also said in the first part of this talk is that if you look at this slice where it disconnects through the singularity, then actually if you just look at the radiation would predict that there's no interior, essentially because of what Netta said. It's pure and it's simple to verify that it's pure. So if you want to talk about semi-classical physics in the interior on this slice sigma 2, so i.e. the semi-classical physics that a semi-classical observer would see when they're on this interior part, then you can just use the radiation. That's all I'm saying. So, and you can just use the radiation, and in particular, you can't trust what an observer outside here would say. Okay, so encoding breaks when the black hole is fully evaporated, and so this distinction of where the observer is important. So at this point, we may get worried, because if we're starting to say that physics depends on the observer, you know, that an observer observing the radiation at full evaporation from the outside would say there's no interior, but then an observer in the interior would say, oh, there is an interior. Then what happens when these observers communicate? What happens when you try to compare notes and agree on the results of the physics? We like to agree on the results of physics. Well, here, the idea that seems to be saving us is the idea of complementarity. So this was an idea that was proposed by Susskind, Thorlacius, and Uglum in '93. And what complementarity says is that it's fine for observers to disagree on the physics as long as they cannot communicate in the future. So I should say at this point that originally complementarity was actually proposed for explaining the whole information paradox. It was saying that, okay, maybe someone thinks that the radiation is more entangled than the other, but that's fine because the person who thinks that the radiation is more entangled has jumped into the black hole. But later on, it was realized that this idea alone could not evade the firewall paradox. Okay, and so at this point, when people realize that, oh, actually, there's this firewall paradox that can be phrased, and you know that complementarity cannot save us from, then you know we should actually maybe abandon this idea and try to do new things. And we actually learned from these page curve derivations that we don't actually need complementarity for an evaporating black hole up to the very late stages, because we can reconstruct the interior directly from the radiation, and they're actually identified. However, here, in the case of the closed universe, or in the case of full evaporation, it seems that complementarity seems to be revived. And so that's something that we studied with Neda and Daniel over the summer. So this is all a very nice conceptual stories, but how do we put some math on top of this? How do we actually do calculations to see if this idea holds water? Well, the idea is that we don't know, but some rules have been proposed, and they seem to be giving us answers that we like. So maybe we should take them seriously. So there's essentially two sets of rules that have been proposed in the beginning of this year. One of them was by Harlow, Zaciuk, and Zhao. And the idea of this rule was to say that we were going to treat an observer in a closed universe differently by passing them through a quantum to classical channel. And the role of this quantum to classical channel was to force the decoherence of this observer. So this is a violation of quantum mechanics. It's not what we usually do in quantum mechanics, yet it seems to be getting rid of our problems with one-dimensional Hilbert spaces. And once we do this rule, it looks like the observer actually sees semi-classical physics. A very related rule was proposed by a group in Berkeley, where what they did is that they imposed the presence of a world line defect in the gravitational path. And the idea of this world line defect is that it was sort of supposed to mimic the presence of an observer at all times. And it turns out that once again, if you modify the gravitational pathing rule by doing this, you find results that are consistent with semi-classical physics again, that no longer predict a one-dimensional Hilbert space. I should say that these two rules are different, but they're very closely related. In particular, if you take the limit of the first rule, where the observer's entropy goes to infinity, you recover the second rule. Okay, so let's see how this pans out. So a few months ago, we published a paper with Neda and Daniel, whose goal was to basically apply the observer rule to the two cases that I described today and try to see what the prediction of this observer rule would be for physics in the closed universe. So we took two observers, alpha and beta. For example, in the ADS CFT example, we put alpha in the outside and beta in the closed universe. And so alpha, who's outside in the closed universe, if you apply the observer rule to alpha, the prediction for the dimension of the Hilbert space of the closed universe to alpha will be 1. Okay, alpha will think there is no closed universe. Essentially, alpha will agree with ADS CFT. But then if we apply the observer rule to beta, who's inside the closed universe, then beta will see semi-classical physics in the closed universe. So they will see a large approximate Hilbert space of states of dimensions set by E to their own entropy. And so it seems that this observer rule recovers semi-classical physics for beta, and beta thinks that it's entangled with ADS and so on. And of course, because they're in disconnected components of space-time, they cannot communicate. So this is fine. We should not worry too much because we can apply the principle of complementarity. The story for the evaporating black hole is similar. So you can think of an observer alpha who stays outside at all times and an observer beta who jumps in. And what the page curve calculation taught us is that on the slice sigma 1 here, on the partially evaporated slice, alpha can describe the experience of beta up to very small errors in the entropy of the black hole. So there you don't really need to worry about who's alpha, who's beta. But at full evaporation, the situation changes because alpha thinks that there is nothing inside the black hole. So that's the statement that they can really easily see that the radiation is pure. Whereas beta will see a semi-classical closed universe once again. So by applying these observer rules, you get these predictions that are consistent with our expectations.
So nothing changes at the page time.
What do you mean?
I mean, when alpha is the outside person, no observer. So, but after the page time, from what you were saying before, the states are entangled inside and outside.
It's more than so something conceptually important changes at the at the page time. It's not what I'm talking about here, but what changes at the page time is that before the page time, it's not right to think of the interior and the radiation as being holographically dual to each other. Okay, they're just separate systems. After the page time, the interior becomes the radiation. They're no longer separate systems. That's what changes.
I'm just trying to agree that doesn't, alpha doesn't. Once there isn't that separation, why can't alpha know everything about beta? Why do you say it's only up to order e to the minus s?
Oh, okay, sorry. There's two things here. One of them is the holographic duality, which is supposed to be exact. The other one is semi-classical physics, okay? Semi-classical physics, I really mean just quantum field theory on a curved spacetime. We don't expect that the actual theory describing what's in the interior is exactly semi-classical physics. There will be non-perturbative corrections coming from quantum gravity effects that will go beyond semi-classical physics. Those are the errors. They're not the duality. Okay, maybe let me, because I'm running out of time. So I just want to give a brief outlook on this. Okay, so what we've learned is that it looks like introducing an observer sheds some light on this one-dimensional Hilbert space problem, and in particular that the real interpretation of this crazy statement that the Hilbert space of a closed universe is one-dimensional is not that there is no physics in a closed universe. It is just that an observer outside of a closed universe does not have access to any physics inside the closed universe. So I hope that this makes you feel a bit better about the statement. Okay, so what is the outlook? Well, I think since these observer rules have been proposed and they seem to be giving us a lot of interesting things, but we don't understand them yet, there's a lot of exciting directions to pursue. So one obvious one is cosmology. Of course, lots of models of cosmology are based on closed universes, and our own universe could very well be closed. So, you know, in particular, de Sitter space is an interesting working example. How can we understand de Sitter space from this observer rule story? What does this all mean in DS? And especially, how about inflationary cosmology? So we really like this idea of the multiverse, especially in string theory, because eternal inflation provides a mechanism to populate the string landscape and to explain things like the cosmological constant problem. But you know, how does this whole eternal inflation story react with this observer rule? It seems that there's an interesting story there. So that's something to be studied further. Then there's a separate question, which I guess goes back to what Dane was asking, which is that if we use the traditional rules of ADS-CFT, we don't get an emergent closed universe. So then what do we need to do? What do we need to change about ADS-CFT to get the closed universe? Well, one thing we could say is just, this is just not what ADS-CFT describes, and this could very well be the right conclusion, but it's an interesting question to ask how to reproduce these observer rules using ADS-CFT directly. In particular to reproduce the point of view of an observer beta who sees semi-classical physics. I don't have anything more precise to say. I'm not even convinced that this will work, but if anything's going to work, I think it's going to have to involve some coarse graining. Okay, so there's been some various proposals. People have proposed, like Dane, to coarse grain over the states. Other people have proposed to coarse grain over the value of n, although both these approaches have some unclear features that it's not clear if they're going to be surmountable. But if anything's going to work, it's probably going to have to do with coarse graining. And anyway, it would clarify the status of ADS-CFT in this whole story. But finally, because this whole discussion has been fairly qualitative, and I'm actually a mathematical physicist, I want to end up by pointing out that I think that there's great mathematical physics to be done there. So mathematically, although this was all very qualitative, there's one clear conclusion, which is that the Hilbert space is not enough to account for situations that involve complementarity. Because once you have complementarity, we saw that the dimension of the Hilbert space can change vastly depending on the observer. Another way to say this is that there seems to be a category error in the way we have been thinking about quantum gravity. Usually, in a usual quantum theory, the Hilbert space is the starting point, but complementarity requires another starting point from which different Hilbert spaces would emerge. And I think it's a very exciting opportunity for mathematical physics. Thank you.
Thanks, Elliott. That was an amazing talk. Since we're we're right on time. Good job. Maybe 1 or 2 questions.
A quick question. So observationally, right, in terms of testing whether the universe, measurements of spatial curvature are degenerate with evolving dark energy. So it's going to be difficult for you.
Yeah, I'm not making any experimental claims at this point. I don't know. Maybe we will learn something about the multiverse that we will be able to see in the CMB, but I think it's way too premature to make any connection to experiments.
I was just curious whether there was some.
Yeah, at least one thing that we're actually thinking about with Neta at the moment is, in principle, if you had the infinite access to infinite technology, would you be able to falsify these types of things or not? But that's how far we are, and it's not very far. So, yeah. Well, I think this observer rule is modifying quantum mechanics, in the sense that it's not the usual rules. However, it's modifying quantum mechanics in a way that the theory that you will get will agree with quantum mechanics up to exponentially small errors in the entropy of the observer.
So if one is going to, quantum mechanics is very rigidly insisted on in the picture of the page curve and the So isn't there some tension between formalism that purports to explain the page curve by insisting on standard unmodified quantum mechanics, but then is forced to then the conclusions that come from that force us to modify quantum?
Yeah, I really think it depends on which modification we will actually need to be doing. You could imagine that there's a rigid framework too that just englobes quantum mechanics, where you would actually be able to take into account different observers' perspectives. I think this is a very interesting question, and it also boils down to the fact that these observer rules are very heuristic so far, so we don't have a first principle understanding of them. Nonetheless, what I will say is that, this is not made to explain the page curve. This is made to explain our new understanding of the page curve that we got from these recent papers, consistent with the fact that an observer in the interior should experience semi-classical physics, even when we choose to put them on the slice that goes through the singularity. But I don't have anything more precise to say.
Sure, is there a question on Zoom?
So Daniel Tapia asks, would the interpretation of S defined at the beginning depend on the quantum mechanical interpretation used? So I think this is related to
the definition of S,
entropy
and of the black hole.
The black hole entropy, I think he's asking.
Yeah. So, well, the black hole entropy is based on a Hilbert space interpretation. So, I'm not sure what they mean by quantum mechanical interpretation. But what I will say is that, yeah, the definition of black hole entropy is ingrained in the usual rules of quantum mechanics. Now, there's a scale that's a bit more interesting, which is this entropy of the observer that suppresses the errors in the case where you do these observer rules. It's not clear what the entropy of the observer is from first principles. So we need to define this in terms of a Hilbert space dimension or something else. I think it's not totally clear at this point. But, yeah.
Let's thank the speaker again. If you have questions.
Very nice. Thank you.